Um, Welcome, everyone. Thank you for coming. I'm very excited. We're going to talk portables today. And portables are everywhere in hospitals now. They're point of care, and they're inexpensive, and it allows a physician to quickly take a look at a patient who comes in, say, with stomach pain. So they're everywhere, and not many people out there repair them. So what we're going to talk about today, or going to start off, is just basic ultrasound and how they work. This is any ultrasound, and you're going to see then, as we follow into portables, that they work the same way, and give you some opportunities on how to troubleshoot them. We're going to talk about some of the component level, on the board level. Boards in this specifically, I have the S-Nerve with me. I can't count 20 some different site models out there. We're concentrating on the S-Nerve today, but some of them are very, very similar. The M-Turbo, the Micromax, the S-Nerve, they're very similar systems. So the nice thing about a portable also is as we finish up today, we'll have a little bit of time to come up and look at it. They're very simplistic systems. They're easy to learn how to use. They don't have a lot of the knobology that some of the bigger systems have. So it's a nice way to enter into the ultrasound learning about them because they are fairly simple. So let's get started here. Again, my name is Jim Rickner. I'm the Director of Training at Conquest Imaging. And just a little bit of exciting news from us is for those of you who have these sites in your hospitals and your facilities, we have just recently purchased a company about 3 months ago, and we have now entered into the market of being able to repair portables as well as sonosite probes. And so this will be an opportunity for you guys to get your portable repaired and your probes saving a considerable amount of money. So we're really excited about that. Let's get started. We're going to talk about how ultrasound works, front end, back end, and power. And then we're going to get in specifically into the sonosite. Sorry about the screen getting cut a little bit. We tried to adjust that, and John finally gave up. But we can get the gist of it. If any of you want a copy of this presentation, clearly I can't bring a workbook for everybody. But if you just email me, my contact information is just jrickner@conquestimaging.com. And it's right there in fact, jrickner@conquestimaging.com. Email me. Some of you are in the class, you want a copy of the presentation, we'll give you an electronic version so you can see and have this for your own reference. Let's talk about building blocks of ultrasound. Pretty much ultrasound, they all work the same way. And the funny thing is the OEMs, they change the names of the same thing to keep us all confused. But in reality, they all do the same thing. For example, front end, scanner, coherent image former, acquisition subsystem, they're all the same thing. Front end is a GE term. Coherent image former is a Siemens or Accuson term. Acquisition subsystem is Philips, but they're all the same thing. In the industry, we call the front end. This is where your signal is acquired. This is your high voltage going out to your probe, which causes a sound wave, which then interacts with human tissue. It echoes back and strikes the probe, and it generates tiny electrical pulses. All that is part of what we call the front end. So that's what they're talking about here. The reason we bring up the difference in the terminology is because if you're looking in a service manual, and the service manuals for Philips is acquisition subsystem, that may not mean anything to you, but now you have the reference. So front end, back end, this is simply a computer. Anymore, If you want to get really technical, hardly anybody uses anything but Windows anymore. I think the last system out that was released with anything other than Windows was the Active Sequoia using a Linux-based system, but everybody's using Windows. There are different levels, XP 2000, they're up to Windows 7 now. So, but it's a Windows computer now that uses application software on top of it to take that Windows computer and turn it into an ultrasound. So again, you have the different manufacturers. They couldn't possibly call them all the same thing. So you have back end, which is GE, Dynac Workstation, which is Accuson or Siemens, platform subsystem, which is your Philips terminology. Okay. And then you have your power supply subsystem. Goes on and says low voltage and high voltage. Low voltage is simply your logic voltages, okay? Your 3.3s, your 5s, your 10s, your 12s, 13s, whatever that particular manufacturer uses. But they're your logic voltages. Then you have your high voltage. And a lot of people say, well, high voltage is, for your printer, that's 115 volts. And that truly is high voltage, I guess. But when we're talking about high voltage and ultrasound, we're talking about the voltage used to excite the crystals in the probe. Okay, so that's a high voltage we're talking about. This is a high voltage that causes the probe crystals to send out sound waves. Okay, so that's a high voltage we're looking at when we're talking high voltage. These are your three main subsystems on any ultrasound: is power, front end, back end. And I like to try to educate people. When you walk up in front of a system and you're trying to figure out what's going wrong with it, one of the best things or easiest things you can do is try to get rid of 2/3 of your system. Well, I know it's not a power problem, and I know it's not a front end problem. Well, now you're back to only troubleshooting whatever components make up your back end. So that's exactly how I approach any problem when I walk into troubleshoot an ultrasound. I try to get rid of 2 out of the 3 main subsystems. Okay, so really good technique, and unfortunately we don't have time to talk about some of the techniques used to cross out front end versus back end. But that's how I try to approach a problem when I am looking at ultrasound. You have your operating system, as I said, all ultrasounds now are working on Windows and proprietary software for Philips or GE or Toshiba, which is your application software. Transducers or probes are part of your front end. They're a component of your front end. Operating system would be part of your back end because it's part of your computer. Okay. You have your user interface or control panel. Again, part of your back end, even though we separated, this is your user interface and control panel that's running on Windows. How's it all look when you put it together? You have your power supply subsystem. Again, what generates your high, what generates your low. And you have some sort of isolation transformer out there to protect the operator and the patient from accidental shocks. So those are the main components of your power subsystem. You have your front end, you have your back end, and all the other stuff that I'm adding now is still part of your back end. So really, you have this block all the way around is your power. This block here is your front end, and everything else is part of your back end. Okay? So when you're talking operating system or control panel, that's all kind of plugged into your back end, called basically plugged into your computer. Okay? Let's talk about front ends now. And I'm just going to skip to the chase here. Here's the front end. Thank you, Sarah.
Did everyone sign in?
So the generic front end, let's just talk about it so you can kind of understand it a little bit. We have a front end controller. That's a function of the front end that sets up every other board or every other, I hate to say board because these aren't individual boards necessarily. They can all these functions can happen on one board. So it just depends on the system architecture. But every ultrasound system has some function that does front-end control. Whatever board does front-end control, it's the only board that talks to the back end. Okay? So if you know the communication between the front end and back end has been interrupted, you only have three things you need to look at: the back end, where the cable plugs in, cable itself, if it is a cable, a lot of them are, and the board plugs into in the front end. If you go out to like a Logic E9, you have a GFI board, which is your front end controller. You have a cable, and then you have the BEP, the back end processor, your computer. If any communication error occurs, you just have three things you need to worry about: the cable, the front end controller, the GFI, or your computer. So this front end controller is responsible for communication to the back end, and it sets up everything else in the front end. Okay? You have your transmit board or function. Transmit means that's your high voltage, okay? Now, we don't transmit every one of these crystals at exactly the same time. We have to transmit so we can steer the beam and build an image. So we're constantly changing what target and space we're pointing towards, and so we have to change our timing all the time. So that's a part of the transmit board as well. It sets up all the timing for its transmit pulse. Then you have your probe interface, which is the board that the probe actually plugs into, and you'll see a picture on this one. They call that your nest assembly, where it plugs into on an S nerve. But it's a path for the transmit signal. It also IDs your probe. When you plug it in, that board, wherever it plugs into, is responsible for IDing the probe. The path comes back from the probe after it generates a high voltage pulse, then it gets an echo back, it strikes the probe, generating tiny electrical pulses. Those tiny electrical pulses come back into your receive board. It receives them, but they're tiny. It can be up to, let's say, 192 tiny electrical pulses. Well, it has to not only amplify them, it also does what they call time gain compensation, which allows you to get a uniform signal from top to bottom. So you don't have a dark spot right in the middle of your image, or it's too bright at the top. You can actually compensate for that. And the receive board is what does that for us. After it's amplified, time gain compensated, it passes it to a beamformer, and the beamformer digitizes the information and then sums it all up, all 182 channels, and passes it to the front end controller. Why? Because it's the only board that talks to the back end. We have to digitize the data right here because we're getting ready to send it to the computer, and it only understands digital data, not analog data. So that's how every front end in ultrasound works. And the back end, I'm going to kind of skip to the chase again here. The back end is a processor or two processors. They have ultrasounds that have dual processors in them. Some have a single. Image memory, which is your hard drive. That's where all the images are stored. A video processor or graphics card or video card that goes out to a peripheral interface where your mouse, your keyboard, your monitor plug into. Well, what's that sound like? A processor with a hard drive, with a video card, and a monitor, keyboard, mouse, right? That's your Windows computer. And that's what this is right here. This is your Windows computer. Then we add the system master controller. Anybody have any idea what the master controller really is made up of? Anybody have any idea? What changes a Windows computer into an ultrasound? Your application software. Okay? So what we do is we have this Windows computer, and then we add application software, or they call it a shell, because it locks you out of Windows at that point. And when you're locked out of Windows, you can't do a lot of the things they don't want you to do, change resolutions, surf the net, all that stuff that they don't want their operator to do. And it becomes an ultrasound system. So that's what the master controller, that and the input from the operator It tells it what probe it wants to use and so on. Okay? And this is what it all looks like when it comes together. Okay? So again, if you just look at it, you have your voltage, your power supply subsystem, your front end that we just broke down, your back end, which is your Windows computer. But in addition to that, it has your Windows software, your application software, your options are loaded on, and your functions. What can the system do? When you see 2D Doppler, power Doppler, pulse wave Doppler, continuous wave Doppler, all those functions are what's built into the system. You can't change them. If I was to hit this mode button, it would give the list of modes that this system can do. Well, that's them. You can't change it. But the line above that, where it says harmonics and 3D, real-time 3D, those are things you buy extra. So when you buy the machine, it will always be able to do 2D or M mode or Doppler, whatever they built into that particular system. But in order to make it more capable, you'll have to purchase what they call options, and those options will cost extra. Okay, one of the options that you might want to buy, as an example, is Daikon. Okay, so you can hook up to a PAC system and be able to send information to the PAC system rather than storing it under ultrasound. Now, portable systems, keep in mind, don't have a lot of image storage capability because they don't have a hard drive. There's no hard drive in this. So they have very limited storage capability. So having Daikon turned on might be a big factor for you. So you can get it off the system and into a PAC system. So that's how everyone works. But let's talk about, well, we talked about modes. This one has various modes. 2D or B mode, you'll see that they call two-dimensional mode and B mode are the same thing, also known as grayscale. It's basically black and white imaging. There's no color involved with it. There's nothing associated with it. It's just the various shades of gray or grayscale, right? And, brightness mode is it's a basic mode. Every ultrasound will be able to do 2D mode. Doesn't matter. It has to be able to do that. Okay? So it's based on the amplitude of the echo. The larger the echo, the more dense the object. The more dense the object, the wider it will be displayed on here. So as you look at an image on your system, the wider it is, the more dense the object you're looking at is in ultrasound. X-ray is the opposite of that, my understanding. I'm not an X-ray expert engineer, but you have to understand what you're looking at. So the more dense the material, the wider it will be displayed. And it's mapped to different grayscales, meaning you can adjust your grayscale to look different ways. Different sonographers, different technologists will have different, they look at things differently. They have a different set of eyes. So they can change to a different grayscale and make it look the way they like to see it. And it tells you the lighter and the darker right there. You can use it for location and measurement. It can be used with any other imaging mode, almost any other imaging mode. I say imaging mode, be careful with that, because there's a mode in ultrasound called continuous wave Doppler. And continuous wave Doppler is not an imaging mode. And so 2D won't be used with it because 2D is an imaging mode. So when they're saying is here, you'll have color. If I changed into color right now, it would still have the 2D image up there. They would just overlay color on top of the 2D black and white or grayscale image. Okay? So you're not changing anything. It's being used with color. Here's a B mode picture. These are known as annotations, which you can see. They'll be defined here. The marker shows you the orientation of the probe. Here's your marker on the screen here. And it tells you that on the probe, it also has a marker on the edge of it. One edge is clean, where the other has a line on it. Okay, you want to orient the probe the same way it is on the screen. If you have it backwards, your image will be reversed. So that's what the marker is used for. You have what probe you're using, what preset you're using, and then the annotations tell you it's common, internal, the bifurcation, and the external. So it tells you this is a way the sonographer can take an image and help the doctor know exactly what they're seeing. Okay, this is what I'm looking at. We don't have time to talk about Doppler today, but realize that Doppler is a different type of mode. When we talk 2D, 2D was based on the amplitude of the echo, so the more dense, larger the echo. Doppler is based on frequency shift. It's blood flow. That's what we use Doppler for, okay? And the way I can define Doppler without going deep into it is if you're standing on the street corner and a motorcycle passes you by, it goes, or did the motorcycle sound change any? No. But as reference to you, as it moved towards you, it had a higher frequency because you were compressing the sound wave. As it got past you and went by you, sound wave gets stretched out and becomes a lower frequency, even though the motorcycles make the exact same sound. Well, we do the same thing with blood flow. If blood flow is moving towards the transducer, the frequency will go up. If it's moving away from the probe, frequency will go down. We measure the difference, and we know how fast blood flow is moving. So that's really what Doppler is. We have color, we have power, we have pulse wave, continuous wave, and it requires relative motion. That's a key to it. And it's different shades. It can be color or not. It can be, and you'll see right here, here's a picture of color. Okay? And this tells you it's red, and so red would be in this area here. It's a positive number, so it's moving towards the transducer. Down here, this is negative, so if it was bluish in color, it would be moving away from the transducer. So that's how we get our information. Colored box, you can enlarge it, you can move it. You have your scale, you have your marker. And again, I wish I could go through all these. I just want to let you know that they're out there. This M mode is a cardiac mode, and it allows us to measure abnormalities in the heart. That's really reserved to a cardiac system. So if it's not a cardiac system, you probably won't have M mode enabled. This is what M mode looks like. So again, you have your focal point. This would be a heart valve right there, and this is based on tissue movement. And you know, I've been doing this for over 12 years now. I don't know how to interpret this, so don't worry about the fact that if you go in and they're saying my M mode is not working correct. What you're going to be diagnosing is noise in this portion of the speckles that are there that shouldn't be there, lines going through it. They're going to tell you what they don't like about it. You don't have to interpret this, okay? So don't. A lot of people get wrapped around the axle on, wow, you know, I don't know what it's really telling me here. But we're not there to interpret the results. We're there to fix a particular problem with it. So don't let the fact that you don't know how to interpret that bother you. It talks about the marker again, the depth, the focal point, and your traces. Pulse wave, continuous wave, they're basically the same thing. They're trying to measure blood flow. Here's a good example of PW right here, pulse wave. Again, you can see the peaks right here. So blood flow is maxing out at about 120 centimeters per second. It's above this baseline, so it's moving towards the transducer. This color kind of indicates that it is also moving towards the transducer. So you have two different indications, both on they call this spectral data. This is color Doppler. This is spectral Doppler. So you have two different indications that it's moving towards the transducer and at what speed. Again, you know, you may not be able to interpret this result other than I can see that peaks out at about 120 centimeters per second. But what you're going to be looking for is noise or lines that aren't supposed to be there, and then what's causing them. Harmonic imaging. This is for the technically difficult patients, and technically difficult is really defined as obese, okay, hard to scan. Okay, so what do we have to do? One of the principles of ultrasound, if we don't have time, is we need a low-frequency probe to penetrate a long ways, but a low-frequency probe gives us poor resolution, so we don't get a good picture. Well, if we have a technically difficult patient, we have to sacrifice image quality for the penetration capability. Well, harmonic imaging kind of does the best of both worlds. We transmit at a low frequency and receive at a higher frequency. So the transmits at 1 and receives at twice the transmit frequency. So it helps us improve our image. And here's an example of what harmonic imaging. If I ask each one of you to look at these images and tell me which one's better, I'd probably get a variety of answers. Some would say left, some would say right. But harmonic imaging is turned on this one and not on this one. And they say, well, I have better image. You know, up here, I can see things pretty clear, where up here they're not as detailed. But if you look down here, these are very nice, you know, dots. They're very resolved. Where down here, they're smeared a little bit. And that's where harmonic imaging comes in, is it's looking at the deep region, not at the shallow region. If you were looking up here, you would be using a different probe, a different frequency, a better image, and you wouldn't have to worry about it. But because we're specifically looking deep, that's why it's better down there. Okay, so now we're going to get into the actual S nerve. Talked a little bit about functionalities on everyone and how they all work, but what about the S nerve? Here's an S nerve picture of it. Here it is live in person. The S nerve, or the S series, is meant to be mounted to a cart. Okay? You won't see these, even though it's a portable system that you can see here. It's not intended to just be sat on a desk, because it doesn't work that way. It's not built that way. They designed it to be put on this cart just like it is here. Okay? And, you know, came out in 1999, Sonocyte did. It was an ATL spinoff. They're really popular because of their cost. They're easy to use. They come with a 5-year warranty right out of Sonocyte. This doesn't work. Sonocyte sends you a loaner, and you send us in for repair. Okay? And if they can't repair it, then we keep the loaner and off you go until the 5 years is up. And then what they want you to do is trade that one in for the newer series they have out there, and we'll get another 5 years. And that's kind of an expensive proposition to buy a new system every 5 years. So again, this is where we came in and saw a pain point in the market, and now we're doing repairs on portables after the 5 years. We're repairing the probes now, and that results in a huge cost savings. So you gotta make sure you're looking into that as an option. Hardware theory, we have front end, back end, and power. Okay? Front end consists of the transducer, the acquisition, and processing. We have to take the data and digitize it before we send it to the back end. Okay? We have our back end, which is a control system, user interface, and display. Now, control system, this is what we call our master controller. It sets up everything else. In this case, you're going to see we have a single board that does both front end and back end capabilities. They do both. And it has these 7 functional groups, if you want to call them control, which is your CPU, memory, video, everything, permanent image storage, it has ports on it. So it's a control. You have your user interface. Clearly, it's very simplistic, which is nice for us. You don't have a lot to worry about or use. I walked up the very first time I ever saw one of these, and I went, oh, I don't have to do anything. But I mean, you have a power button that's clearly marked. It's got the universal symbol, power. Everything's marked. It has 4 pages down here. You go to page 1, 2, 3, 4. You have imaging mode options. It's all real simple stuff to use when you're talking ultrasound. So again, if you get the opportunity, you've never worked with ultrasound, you don't have the experience with ultrasound, find it portable and break into it that way because it's a really easy way to get to know some of the functionalities and build yourself into ultrasound. Power, again, we talk about power, you'll see this has one board that handles all of your power. And I apologize, it's normally it fits on the screen, we tried. But we have our acquisition subsystem here, our processing subsystem, which is where we take our raw data and digitize it prior to passing it to the back end. We have our control system, which is part of our back end, then our user interface. Then we have our power supply. So this is all what we talked about earlier, power, front end, back end, and how it all comes together. Well, here you go. Here's your power board. You can see there's your Nest assembly, your Nest box. So that's where your probe plugs into. That's what I'm plugged into right back here in towards the end of the class. I hope that you guys come up and look. But that's where your probe plugs into. Then you have your power board. And on this one does not have this mini dock assembly, but Nestner, but your in turbo would have that, which is very similar, same motherboard. And then you have SD cards. Now these are oftentimes or should be covered with copper tape to keep them secure and protected. This picture shows it without the copper tape, okay? But that's where your SD cards, which is your storage, really. Then your main PC is that board that they all mount to. Front-end components, again, we're talking real simple. What are the front-end components? We have the transducer, and we have what they call the acquisition board, which is all where your beamforming goes, your transmit, your receive, everything's done on one board here. So it makes it real simple for you. And processing, this is that pre-processing we talked about, that we actually digitize the information so that we can then use our computer to process it even further and get it displayed on our monitor. And really, there's your front end right there. Now, when I say there's your front end, keep in mind that this main board here also does some of your back end processing for you. And that's your most common failure of all the boards, okay? So there's your Nest assembly. That's where the probe plugs into. Let's talk about back end again. We have our display, our control. That's what, it's a master controller and our user interface. That's all made up of, basically a computer, and they call that the back end. It doesn't have a standard keyboard. However, you can plug one in via USB port if you want to do something that makes type a little easier. There's some data input that, like when you're building your network, you have to do some typing. Well, this doesn't have a keyboard, so you have to use a mouse and go to each letter and type it in. But you can plug in a standard keyboard and do the typing for you. So even though it doesn't come with one, you certainly have the option of plugging one in. And there's your UI. Power switch, control keys, again, very simple, very easy to use. Touchpad. And we have a battery. You can see the battery is right here. Now, it's optional most of them have the battery pack installed in it. But again, it doesn't have to be used because it's really designed to be used on a cart, and carts are normally plugged in. So can you use it without, if you have the option? Yes. But in reality, this one's really designed to be plugged in. Transducer connection, you just have this little tab here that folds out and you rotate it and it pops off. It's real simple, real easy to use. Again, if you get a chance to use this, come up, that'd be great. It does have USB, like I said, so you can plug in the keyboard. You can export clips to a thumb drive, sure. You can also export your network settings to a thumb drive so that you can have those saved outside of the device itself. You can't use password protected USBs because this one will allow it. And it tells you don't remove it while it's being used while it is actually exporting because it can damage the USB, which will result in loss of patient data. So make sure that it's done doing what you set out to do prior to ejecting it. Okay. Some pictures of some of the boards and what they do. You have the control panel. And I can't read all of these. I apologize. But we're going to go through these. This is your I/O board right here, and you'll see better pictures of these. There's your LCD backlight inverter, okay. High voltage board. But the good news is you can't really hurt yourself on this board because by the time you get access to it, the system is not operational. So you can't really hurt yourself unless you have a gym. There's your SD cards. 4 slots available. Power distribution, it's a super simple power distribution. We've already kind of talked about it. You have a battery, okay, you have your external source, which is your wall, and your power supply, which is one board in your system. And there's your one board, that is all your power, logic, and high voltage. So it mounts right to your main board. This is another, I said the main board is your highest failing item. This is the second highest failing item from a PCB standpoint. The I/O board is pretty resilient unless you physically damage because you get to unplug it from the wall and they start taking the portable and yank your cord out and damages the port. Other than that, it's very resilient. So there's your battery pack. Should be able to recharge it within 5 hours if it was fully discharged. Can run about 2 hours. Normal power on, and we're not going to really talk about this, but the on-off functionality in this is very simple. You hit the power button, it turns off. When you're actually using this, if you're using it, for example, to set up Daikon, you want to go in and modify your Daikon settings. When you first turn it on, it won't let you get into Daikon because it's not fully booted. Even though you'll see the image, they're trying to speed up the boot process so you can get to imaging faster, but it doesn't mean that you have all the functionalities that will be there in just a minute or two after that. So I've gone in, turned on the system, went in and tried to adjust Daikon. That's not available. Just give it a couple minutes and then come back. It won't bother you. We're not going to spend a lot of time on connectivity because it's kind of complex or long, and you don't have that kind of time. But I do want to make sure that we cover some of it because it is important. This particular system, as an example, when I got it into my shop, I was disappointed to find out that Daikon is not turned on in the system. So why wouldn't Daikon be available on the system? Anybody remember what I said earlier? We didn't buy the option, right? We didn't buy this new, but we bought it from our vendor, and whoever had it previously never bought the option for Daikon. So the only way they can get patient data off is by plugging a thumb drive in, downloading it, and carrying it somewhere else, right? Because they never bought the Daikon option. So some of these things that I'll be talking about, we can't do on this system because it doesn't have Daikon turned on. Okay, you're going to need a few things, and this is all part of what your IT department would give you. Your name, your IP address, subnet mask, where you're going to be sending to, if you're going to be sending out to destination devices. And then you're going to want to have AE titles and network port numbers. These can support wireless, but you're going to have your wireless settings if you're doing it that way. If you're sending to a printer, you're going to have to know that information. Printers are all different from a network Daikon perspective. They have different settings. So you're going to have to know what the settings are for that particular make and model of printer. Default gateway, admin password, and you need to be able to log into the system. Now, I want to say something about this system, okay? If you go in, for example, the options, and you say, well, I want to look at my setup, one of the very top ones is admin, and it's going to ask you for a password on that. Okay? Don't let that bother you. Whoever your lead is will have an admin password. You get it from them. But the only thing that you really have access to in this admin is not what they're talking about here on Daikon, but it gives you the ability to add users and give those users a level of authority. So that's the only thing you're missing if you don't have access to admin, is you won't be able to add users, you won't be able to change their authority and what they can or cannot do. These are some tools that you should carry with you if you're working on ultrasound. We have what we call Conquest Daikon server. We didn't make it. I don't know why it got called Conquest. UC Davis developed it. They named it Conquest. It's a very simplistic Daikon server. What do I mean by simplistic Daikon server? It means if you have a laptop, I carry a Windows XP laptop with me everywhere I go, and I have this Daikon server software. I can plug my laptop into the system, set it up just like the PAC system that they're trying to send to, and then send to my laptop. And if the images get to my laptop, I know that my system's working fine. If it doesn't get to my laptop because I have this PAC software, then I know there's a problem with the system. It's a way for me to tell IT, well, my system's working fine, or my system's not working fine. It helps me. You don't have to use Conquest Daikon. It's free. Again, it's not supported by us. We didn't develop it. But there's other ones out there that are more robust and do more things. Some of them are free, some of them aren't. But all you need is something real simple. The object is it sending images to the laptop and can you interpret it? If you can, the machine's working fine. So that's the intent. Okay? You install it, like I said, on the laptop. It becomes your Daikon server. You just take the settings of where you're sending to off your system, you plug it into your laptop, it becomes where you're sending it to. You can use a switch because it has activity and connectivity lights. It's a wonderful tool along with the laptop to be able to plug into the wall and ping a destination, see if it's accurate. So these are some things that we use and carry with us, a laptop, a network cable that we can either plug into the wall or plug into the system and use a Daikon server software, and with the switch, The switch tells you what speed the network's running at, auto 110. So you have a lot of information if you carry a switch with you. Good troubleshooting device. And in your laptop, you can plug that into the wall, ping a port, and make sure that it's active. So some great tools that you should have if you're working on ultrasound. One of the single biggest things you're going to get calls for in ultrasound is I can't send to my PAC system. I don't know, it just seems to be rampant out there. And it can be as easy as all you have to do is reset the IP address, change it by one, save it, reboot, change it back to what it was, save it, reboot, and it starts working again. It's amazing how, but they just quit working, and then you have to determine is it the system or is it the wall outlet or beyond. So great tools to have. And Daikon setup varies on each one. This is for the S nerve. Very simplistic again. We're not talking, when you look at the GEs, for example, the Logic E9, Logic 9, when you go in and do a Daikon setup, there are like 8 tabs across, and you have to go through, you have to set up the TCP/IP of the device. And the next one is you have to define where you're sending to or importing from. Then the next one is you have to put in the AE title and all this information. Then the next one is you have to do global config. And you're going through none of that here. This is so simple, you can only send to one place. You only have one destination device. So very simple. You can see there's not a lot of buttons you have to worry about. And we're not going to go through each one of these, but I want to make sure that you can see them. You can create backups of the Daikon only, but it does not save the TCP/IP address of the system. So I want to make that sure you understand that. If you export your Daikon settings to a thumb drive, you're not saving this system's TCP/IP address. You're going to have to do a printout, write it down, a picture, whatever, in order to save it. So you can connect wirelessly. I already talked about that. So you do have that port in the back of the system. That's where we're at, connectivity. You can see this is exactly what I'm looking at, and I have my connectivity button on the left-hand side. And it was very simple to get into. Again, when I'm getting there, when I'm done, I go back to imaging. I simply look across the bottom. It says options on the bottom. And it says, what do you want to do? Well, it has review. I don't want to review, annotate. I'm not annotating. What exam do you want to look at or setup? And that's where we're going into the setup. So we hit setup and voila, there's where we're at. Okay. You select connectivity and it gives you the options on the right. Pretty simple setup again. You have these different options, providing you have Daikon turned on. This one wouldn't give me those options because I don't have Daikon. So it goes on, and again, the reason this is here is I don't have time to talk about everyone and how to do it. But what I wanted to include and kind of talk to you guys about is if you do send me an email just saying I was at your class, you'll have it here in writing, so now you can follow it if you're ever in front of a system. So there is use to having it in this. I just don't have, this is a day-long class normally. Back at Conquest, where we talk a lot more in depth about each one of these and how we can use it. Again, the reason we're bringing Daikon into this is it's one of the single highest failures in ultrasound is talking network settings. I can't send, I can't retrieve. And they can be quite tricky because, I don't know what kind of relationship you guys have with your IT department, but my relationship as I travel throughout the nation's facilities working on systems like this is IT department saying, it's not us, it's working fine. I'm saying, well, it's not me, it's working fine. It's not us, it's working fine. It's not me, because every you do that game all day long, right? So that's why we're trying to talk about this. I know it's some information. But you have locations, you want to be able to configure different locations to send it to. You have archives, which is again where you're permanently storing patient data. Configures printers, configures Daikon printers. And again, they're a little messy because each one has its own settings. Storage commit. Storage commit is the same thing as an archive. And when we're talking storage versus storage commit is the same thing. The only advantage to a storage commit is that when you send patient data to a PAC server, that PAC server, if it's a storage commit server, sends a message back to you saying, I received it and it's good. So you can immediately delete that patient knowing that you got a warm fuzzy that they received it and it's good data. Worklist server, this is where you import data from. Okay, this is so the sonographer doesn't have to, every time a patient comes in, type in the patient name. They just import it. Patient goes into the hospital, checks in at the front of the hospital, all their data goes in, and they say, I'm here for an ultrasound. They come in here, they hit worklist, they query worklist, and it imports all the patients for the day. So they're good to go. That's worklist. It's a great tool. And then you have MPPS, which we're not going to spend enough time on, or any time on today. Setup builds, it goes on talking about how you have to have a unique name. You have to talk about the network location. You have to have an AE title, which is application entity. You have to configure if you're using wireless. You have to have a device port number. Normally, it's 104 for Daikon, but again, your IT people will give you this specific information. Okay, 104 is normally the default for Daikon. They, however, can change that. Desired dynamic host configuration. Almost all ultrasound companies, OEMs, say don't use DHCP, but almost all hospitals use DHCP. It makes it easier for the IT department. They don't have to assign and monitor and track changes. It happens automatically for them. So clearly, if you're in the IT department, you want to use DHCP, but almost all of them tell you not to do it in ultrasound. But everyone gives you the option, so you can't do that. You have to have a default gateway. You have to have a unique address, which has to be unique for the system. And it cannot be 127. 127 is for networks on a specific device. It never leaves this device. Sequoia, as an example, the Axon Sequoia uses 127.0 IP address, and it's for its internal network. It never leaves that device. It can't be used anywhere else. Subnet mask 255, 255. This one says 0.0, and the reason it says that is because for whatever reason, Sonocyte, yes, nerve specifically I know of, and the Micromax set it up as 0.0, which is very unique. Normally they're 255, 255, 255, which limits your network size to 254 devices. This does not limit it to 254. This network, the 255, 255, can have over 60,000 devices on it, which is why I don't understand why they default to this. I've only seen one hospital ever use the 0.0, and when I asked the guy, why would you do that, it was because he had, instead of having less than 254, he had like 260 devices. And so it exceeded the capability of 255, 255, 255. And rather than create another network with routers involved, he just said, I'm going to add the ability to add those devices on a single network. Very unusual, but that's what this defaults to. So you need to make sure that you correct that if you're setting up the network and you have a standard gateway or mask. Default gateway, again, is 127. Normally ends in .1, but that's again your IT department should provide that. Okay, we have different fields you're going to have to fill in. This is where I don't really want to get into each field that you'll have the ability to change. But you can specify when you want to send images. Every time you get an image store, or do you want to wait till the end of the study and send all the images you took? Okay. Network speed, again, you select auto. Something that on the SNR you don't want to do is select the 10 megabyte full or half duplex, excuse me, because for whatever reason, I don't know the reason specifically, but it causes the system to become unstable. So they specifically tell you in the manual, user manual, and service manual, don't use these things. Compression, timeout, we're both read and write. So it gives you these settings that you can adjust to make it work the way you would like it to work. And then it goes on and talks about different security protocols you might be using and how you can adjust those. And lastly, it tells you it continues on with authentication and stuff. Again, these are all the fields that your network administrator will be able to help you with and give you very specific information on. You don't just have to plug and play. Then it talks about archive. So archiving is storage or storage commit. It tells you the things you'll need, the name, the IP address, port, AE title, and determine which IP is successful. And it will tell you if it passed or failed. Goes on and gives you the more selections that you can set up. And then it has printer setups, so you can set up different printers. Again, these are things that you'll encounter if you're working on ultrasound. They'll ask you to do these things as they maybe add a device or something. So I wanted to provide this information for you. But I'm not going to go through each one and how you set up each different type of printer. But this gives you some ideas and questions they'll ask. 3 pages. And then again, storage commit, same thing as an archive. I'm not going to go through it again. But it's the same thing as an archive, except it sends a message back to the system. Work list, we already talked about work list. That's where you import data to the machine as opposed to having input every one. Very cool system. I love work list when it works. When it doesn't work, it becomes a pain. And APPS, not many people use that, not many hospitals yet. So I don't really spend any time on it. If you have it, your IT department will certainly let you know and tell you what you need. One of the cool things is if you have multiple systems, multiple SNR systems in this case, you can take configuration off of one and put it on another. Anybody have any idea why that's useful?
It takes a while to create 3 steps.
Does that? This is specifically now, you're right, but remember this is specifically configuration. It's only your network configuration. But why would you want to import data from a different system onto this one? You're replacing it? That'd be a good one. Getting a loaner? Absolutely. You'd be getting a loaner, which brings you to another reason. Why are you getting a loaner? Because it's not working. You don't know why it's not working, but the one right here is working. So you take the configuration off the bit, put it on this, and see if it works. If it does work, we know it's a configuration problem with something in your network on the system that you fix by importing somebody else's configuration. Okay, so there's a lot of reasons to want to do it, but be careful when you are doing it because you can come up with conflicts then, because what you're doing is you're creating two systems that are the same from a network perspective. And don't remove the USB while you're importing it. It does cause a series of reboots when you import data. It will make you reboot, deactivate one network and activate the next one. So it will restart in a couple of weeks. Preventative maintenance. Guys, has anybody worked on ultrasound here? Okay, so preventative maintenance. What do you suppose preventative maintenance on this is?
Put it on the physical inspection.
That's great. I like that. Phantom, physical inspection. Anything else?
Clean it,
Clean it.
delete old data.
You could delete, but in this case, probably not going to have any because it's limited to the SD card, and it won't work unless you get rid of the data. It work. So they're going to yes. So that's a good idea.
Calibration?
I'm sorry?
Calibration?
Calibration, there's something I wanted to hear. You can't calibrate this. And worse or better, how you guys want to look at it, the manufacturer here tells you that there's no PM required. You don't even have to PM this in. And now they didn't go on to say that some facilities may require something that wasn't mentioned yet. But you're near electrical safety.
The probes.
Absolutely. And that's something, I like that because he said probes. I travel all over and I've got 90% of the hospitals that I visit they do electrical safety on the system, they don't check the probes. And yet that's the one thing that they put on a patient, right? Patient GE tells you to check electrical safety on the system in 3 locations. An exposed screw on the monitor, where the probe plugs in, and exposed metal on the caster. And I always kind of laugh, how many patients have you seen laying on the floor holding on to an exposed piece of metal on the caster so they can get shot, right? While they're holding on to something else, okay? But they require that. Here, we're not even checking the probe. So really, really, really need to check the probes, okay? Because that's really where the rubber meets the road, so to speak. No, if there is, it's a problem. No, that's a good question. What you have is you have a phantom. We use a phantom. You can use a tub of water if you want. You don't drop the whole probe in. I've had that happen. Seen it happen. But what you want to do is you hook up your electrical safety analyzer. You put it in enclosure leakage mode so that your clamp is now inside the water, the bath of water, and you submerge the lens that is touching the patient. You submerge the lens in there and you lift ground. And it'll tell you exactly how much how many amps this probe is taking through the safety analyzer. So you do that, and it's super simple. It's not like it's a time consuming that much unless I went to Johns Hopkins 2 years ago to work on their equipment and show them how to do PMs on their biomedical department. And the very first one they had me show them on demonstrate was on IV22 with 26 probes. 26 probes in one system. Still a record by far. I'm used to 6 on a really bad day. They roll in this car, has 26 probes in it, you have doors in it. Who has 26 probes in one machine? But that's how you do it. It's real simple. Once you hook up your safety analyzer, you drop it in the bath, enclosure leakage to the ground, and it leaks. So, real simple procedure. But preventative maintenance, again, manufacturer doesn't require any. There are no filters. nothing that you can really do. Patient data would be great to delete, except it really doesn't have much in the way of storage to begin with. And, you know, some of your hospitals will require electrical safety testing. I think that's a great thing, as long as you're testing the probes. Okay?
When you're testing the probe, is there a specific kind of water that you should be using? Because distilled water wouldn't conduct.
That's exactly right. You know, the actual, most manufacturers tell you to use the saline solution. They'll even tell you the percentage of salt to water they want you to add. I've done that, and it's okay. But I've done just tap water versus saline, and the results don't change. So you don't want to use distilled water. Just tap water works fine. If you want to add salt to it, it just makes it a little more messy. You have to rinse it down. You have to make sure that the salt doesn't stay on part of it. But, if you want to add saline, it's great. If not, just use tap water. So definitely don't use distilled water. But important, okay? Electrical safety, I can't. To me, that's that key. What about backing up? Don't you want to back this up?
No.
The only thing you can back up is your network settings, so you're really limited in what you can do on these, which is good and bad, right? They don't have presets per se to keep you back up. They don't have the traditional backups that you would have on ultrasound. They don't exist on this one, so it's good and bad. Your PM is going to be very, very, very quick. Electrical safety, clean it up, back up your network settings if you want, and off you go.
When you say clean, is there a specific wipe that you recommend that will dissolve the plastic or membrane?
Yeah, I guess the answer I have to that is there are wipes that I recommend not using, which are high in alcohol or hydrogen peroxide, because they will, especially on your touchscreen, start changing that to a milky white, and your touchscreen becomes not functional because of that. But, you know, it really is up to each hospital and what department they're using it in. You know, we use the Epics, Philips Epic system, beautiful system, big old touch panel on it, but if they're using it in a OR room, then they have to use these wipes, and the touch panel lasts for about 2 years, and they have to replace it. And try to tell them, you know, you don't need to. They're worried about killing everything, including the touch panel. So, you know, it's a cost and a trade-off. I wish they had just hit those sticky that they could put over the thing and go into the OR. They're done with the patient, pull it out, put another one on, and that way everything's cool. I would certainly, you know, the $100 you spend over 5 years for those, you know, removable screensavers would certainly save money because the touch panel at this point costs almost $4,000.
Watch the bleach wipes too.
Yeah, bleach wipes, same thing.
I got one.
Anything.
ER, I can scrape with my fingernail. If you actually read instructions on those, after you wipe it, you're supposed to leave it for 5 minutes.
And wipe it off again.
Still water or water on a rag. They never do the second part.
Exactly. I agree. It's hard.
When you're ground check on the probes, how often do you find one that the ground leaks?
There's two, not very often, to be honest with you, but there's two occurrences that I can tell you that will kind of highlight the fact that it absolutely needs to be checked, and that's if you have a section of the lens, we call it delamination. If you have lens missing, even if it's wore out on a corner because they're cleaning it, even though they're using a washcloth, let's say, they act like sandpaper over time. The corners seem to go away first. Other types, when it's just damaged, they peel the lens off. That's gonna result in a lot of times leakage. And the other one is if they drop the probe, they'll crack the case right on the corner. And this one's kind of cool because it has a little bit of plastic before the lens starts, but some of them, the lens goes almost all the way to the edge of the probe. So when they drop it and it lands on a corner, it'll crack right into the corner of the lens. When you put it in that water saline solution, it will get right in there and it will leak. So those two things are pretty good. When you see them, you'll say, I really need to check that. But I've had what looks like a perfectly good probe leak. You can't see any holes, can't see any damage. Stick it in there and it leaks. And that's a problem. Now, just a little, there's different limits for leakage for each type of probe, body floating, cavity floating, all that. But just from my personal experience and what I see, if it's over 10 microamps, it needs to be taken out of service. Because probes are designed to not leak. Okay? They're not supposed to leak. You should have 0 to 2 microamps or more. You stick it in there. If, for example, you lift ground, you have a probe, you have your water bath, and you lift ground and it jumps to 5 microamps, and you put the probe in the bath and it goes to 7 microamps, your leakage is only 2 microamps. Because it was leaking 5 without the probe even involved in the system. So you measure the difference after you put it in, right? But if it's leaking up, or if you lift ground and it's 5 and you drop it in there and it goes to 16 microamps, there's a problem. Even though that's passing electrical safety standards, it's leaking, and you should take it out. And the way I do that is I don't give to my customers. I put the thing right on my service report that says, although this probe passes electrical safety standards, the leakage is unusually high, and this probe should be removed from service and repaired and replaced. So I'm telling them it's passing, but it's not right. So there's 2 messages I'm giving them. So I'm not cheating them out of anything. I'm not trying to sell them a probe, but I know it's unusually high. If you have 10 microamps of leakage, it's not right. Okay? And that's a lawsuit, right? Patient comes in, and you're standing, and you shock them. They know you shocked them, whether it kills them or not. Even if they say, no, that hurt a little bit. Well, now you're up, you're open. So don't like, how are we doing on time? I'm almost done here. I'm going to fly through some of these. So, again, I want you to see what you really need. I also want you to be able to walk up here if you want to and look at some of these connections and such. Different ways to clean transducers right here. Again, rely on what your department says. What you have to know how the transducer is being used and what kind of transducer in the cavity versus body floating versus TE. They're all different, so you'll have different system backup. We already talked about it. You can back up your network settings. You don't have any other where you can back up patient settings, but we as clinical engineers have nothing to do with backing up patient data. Okay? That's a user. That's your technologist's job. You backing up patient data onto a thumb drive just sets yourself up for a HIPAA violation. Okay? Don't do that. I leave anything to do with patient data is on the user. I don't delete it. I don't save it. I can show them how, but I'm not doing it. That's on them. Network settings, so pretty good idea to back them up. But on this system, they're so simple. It's not a lot of work to read manually read. Troubleshooting, we're going to barely spend any time on this. This is common ways. Troubleshooting this, again, is a very simplistic system. But your approach that you should do, you want to ask the right questions to isolate the problem, front end, back end power. front end, back end, hardware versus software issue. Ask the right questions. What are the right questions? What software, hardware options do you have, and which ones are working? So artifact inside the image area, meaning if I was to go in here, is it inside the image area or is it all the way outside of the image area? Okay, that tells you. If it's outside the image area, it can't be a front end problem. Front end doesn't know anything about the rest of the area. It only knows the image, actual image area. Okay? Here, if you get up here, when you get up here, look, there's a pixel missing in this one. Okay, so ACR, American College of Radiology. If that's inside your image area, that's an automatic problem. You have to fix that. If it's outside the image area, they don't care. So that's what you're asking right here is it affecting the entire screen outside the image area or not? That's the right question. Okay? What imaging modes? Is it color? Is it Doppler? Is it 2D only? Want to know which ones are affected? Multiple probes and multiple ports. One of the most fundamental things you ask in ultrasound, this only has a single port, but most of them have 3 ports or 4 ports. So is this artifact that you're seeing in the image area affected by multiple probes in multiple different ports? That helps you isolate it. Intermittent versus constant. We all love intermittent problems, right? Any changes? Is somebody coming up in and done anything different now? Is it stationary versus portable? Portable systems get beat up. They get bounced around through elevators and hallways, and off of walls and doors, and how often you send exams and packs. And again, I'm not going to go through all these. This is just ways for you to look and see, questions you can ask and what you might do in the meantime to check it. And one of the things that they do have in the S nerve is this cover. This is a shield. And if that cover isn't mounted correctly, gets dirty, gets a carbon deposit between it and where it's mounted to, it can induce noise to your image. So this is one of the things that they ask you to check if you're having an image artifact, noise problem. And it tells you some of the system information here. As you highlight the system information, that's really good information. Tells you what version, and it's all listed right here. Sorry. This is one thing. If you do have a problem and your machine's not working, this code right here, it's called an assert code. If you have that assert code because it's given it to you, the screen, that can help us troubleshoot exactly what's going on with your sonocyte. So if you get this screen, which if it's not working, you will get this screen, look for this assert code, and it can be 3 or 4 digits, and let us know what it is. There is no backup except for network settings and patient data. And it tells you how to do it. It's really simple. Import, export. And it goes on USB devices, not working. Parts replacement, again, it's not something we can cover today. But if you request this and get it, it tells you here how to do everything. And I included it because I think it's important. If you want to get in there, it shows you the battery, tells you the 7 screws you have to remove, out, and it tells you here's the things that you need to replace or remove, and it gives you where the screws are located. Just kind of a good little preview of how you would go in and do things if you were trying to get in and work on a S-nerve. Now, the problem with working on these in the field, it's nice to be able to tell you what's going on, be able to do first call, be able to try to work on Daikon and stuff. But even if you said, well, I know it's my power board, good luck finding that power board. The Sonos site does not want to sell it to you because they want your system in. They'll give you a replacement loaner and they'll fix yours if they can. Otherwise, they're going to try to get you to keep the loaner and so on. So even though there's good information on how to take it apart, unless you have a source for the parts, it's difficult at best to find them. So this is just, again, there's your cover over your SD cards with a copper tape. That's not uncommon. So you might see that. Your I/O board and your main board. So, again, I don't want to go into all this, but it will be part of the newest glossary of acronyms. And that's really what I have for you. You guys have any questions for me? Okay?
Probes. How small people are.
Yes. Best practice. Did everybody hear that? Can you swap a probe on any machine with power on? And the answer to that is yes. The best practice is to hit freeze first. But 99.9% of the time, you will not cause any damage to a probe by hot swapping it. But it's better if you just hit the freeze button, which removes high voltage from it and you actually flip it.
Yes, just for storage or the system software.
They are a combination of system software as well as firmware on the boards they have to match. And they do provide the only storage of the system.
So replacing the system.
That's correct.
And then,
What you want to do in that, if you're going to do that, is you need to make sure that you back up the SD card prior to there being any problem with the system. Otherwise, you have to rescue it.
and then patient data will automatically delete when it's transferred on to the investigator.
And that's, again, that's the operator's problem. The most you should ever have to do is demonstrate to a new operator how to do it. But chances are you won't ever have to do that because they didn't become an operator without having some idea. Because I've never had to show them that. Any other questions? Yes.
Is there any place that standards are published for leakage?
Yeah, ACR has some, as well as NFPA 99 has their standards of electrical safety. If you again send me an email, I have what we call our electrical safety checklist. So we fill out every time we do electrical safety all the readings. It's two-sided. On the back side gives you all your limits. So all my engineers have that so they know their limits. Anything else? All right, well, that's all I have. I really appreciate your coming over here to ICE and everything. I do invite you up here to take a look at this if you want. If you have questions, please come on up. But that's all I have. Thanks so much.